Welcome to this presentation on quantum basics made simple, qubit measurement techniques. A classical bit can be either 0 or 1. But a qubit can exist in a superposition of both states. As shown in the figure, when we measure the qubit, we finally obtain a classical result, either 0 or 1. In this video, we will see how an invisible quantum state is converted into a measurable classical result. Presented by Professor Gottapu Sasibhushan Rao. Before measurement, a qubit can exist in a superposition. Its state is written as psi equals alpha times kate 0 plus beta times kate 1. Here, kate 0 and kate 1 are the two computational basis states. Alpha and beta are complex probability amplitudes. Their squared magnitudes satisfy modulus alpha squared plus modulus beta squared equals 1. When measured in the computational basis, modulus alpha squared gives the probability of obtaining 0, and modulus beta squared gives the probability of obtaining 1. The figure shows the qubit state as a point representing a superposition between the two basis states. Psi is equal to alpha 0 plus beta 1. Alpha square plus beta square is equal to 1. Now the question is, why do we need measurement? The qubit state contains the amplitudes alpha and beta. But we cannot directly read these amplitudes like voltage levels in a classical circuit. Measurement provides the bridge from quantum information to classical information. As shown in the figure, the quantum state enters the measurement process and finally gives a detectable result. The observed result is either 0 or 1. Depending on the qubit technology, the physical signal may be magnetic, electrical, optical, or microwave. What happens during qubit measurement? Before measurement, the qubit is in the superposition. When measured in the computational basis, there are two possible outcomes. We obtain 0 with probability, or 1 with probability. The two probabilities add to 1. So measurement changes the superposition into a definite state, either or. This is an important difference from ordinary classical observation. Different qubits require different measurement techniques. As shown here, magnetic measurement is useful for spin-based systems. Electric measurement detects changes in charge. Optical measurement uses light or photon signals. And microwave measurement detects resonance changes, especially in superconducting qubits. The common idea is simple. Qubit state, physical change, detector signal 0 or 1. First, consider magnetic or spin-based measurement. The qubit information is associated with its spin or magnetic moment. As shown in the figure, the qubit spin produces a measurable magnetic response, which is then detected. Spin qubits can use spin-dependent tunneling. NV centers combine microwave excitation with optical readout. NMR systems detect the magnetic response of nuclear spins. So the basic flow is qubit spin state, magnetic response, detection. Next is electric or charge-based measurement. Here, quantum information produces a very small electrical or charge change. As shown in the figure, the qubit state produces a charge response, which is converted into an electrical signal. For charge qubits, a single electron transistor can detect very small charge changes. Spin information can also be converted into a measurable charge difference. So the basic flow is qubit state, charge change, electrical signal. In optical measurement, the qubit state changes how the system interacts with light. For trapped ions, one state may appear bright, while the other appears dark. Quantum dots can produce different photon emission patterns. The figure shows light interacting with the qubit and the resulting photons being detected. So the basic process is qubit state, light interaction, photon detection. Microwave readout is widely used with superconducting qubits. The qubit state slightly changes the resonance of a microwave resonator. As shown in the figure, we send a microwave probe signal into the resonator. The qubit changes the phase or amplitude of the transmitted or reflected signal. By measuring this change, we infer whether the qubit is in state or. So the flow is qubit state, resonance shift, microwave readout. Finally, how do we choose a measurement method? As shown in the figure, several factors are important. We consider the type of qubit, required measurement speed, required fidelity, acceptable disturbance, and the available coupling mechanism. So there is no single measurement method for every qubit. The qubit technology and its physical interaction determine the most suitable measurement technique. Thank you for watching. In this video, we have seen how a qubit state is converted into a measurable classical result using different measurement techniques. In the next video, we will study the Bloch-Sleer and see how the state of a quantum bit, or qubit, can be represented and understood visually. Thank you.